Section 12.5 will look at reduction of alkynes. So I can do the same reaction on an alkyne that I just did. So if I take my alkyne and I treat it with H2 and palladium on carbon, the same reaction will happen. The two hydrogens have to add from the same side, which will give me my Z-alkene because of syn addition of hydrogen. However, alkenes are still quite reactive to H2 and palladium on carbon. And since the palladium on carbon is a catalyst and can't get used up, H2 is a gas and it's actually really hard to control an exact amount of gas in a reaction. What typically happens is that it's going to reduce all the way to the alkane. Really, we cannot stop this reaction. At the alkene. However, what do organic chemists want to do? Organic chemists want to control everything. So now we want to find a way to stop this reaction. So really what the problem is in this reaction is that our catalyst is too good. So let's try to come up with an analysis to find out how to solve this problem. So first of all, we've got a catalyst, and our catalyst is too good. Since the catalyst is too good, it catalyzes the alkyne reaction and the alkene reaction, and we can't get it to stop. So since the catalyst is too good, our next step is find out if there's a way that we can make the catalyst less reactive. And organic chemists sometimes call this poisoning a catalyst. Which really is just deactivating it. It's making it less active. If the catalyst is less active, it has reduced effectiveness. In performing these reactions. So Lindlar came up with a catalyst through extensive trials on it, and figured out that if you took your palladium and put it on calcium carbonate instead of carbon, we added lead acetate, and quinoline, that would make a deactivated catalyst that would stop at the alkene. So if I take my alkyne again, and now I react it with Lindlar's catalyst, and typically that's how I'll write this. I won't write out all the reagents, I'll just write Lindlar's catalyst. It stops at the alkene. Now the question is it going to stop at the Z-alkene or the E-alkene? Well, the mechanism, even though the reagent is different, the mechanism is really the same. We've got a metal catalyst that's coated on some kind of a surface, and it's just being inhibited by these other compounds. So the two hydrogens still have to both add from the same side. So we get the Z-alkene due to syn addition of hydrogen. Of course, what do organic chemists want to do? They want to control everything. So now that I can do that, I want to be able to also make the E-alkene. So there is a way to do that, and we can do it with sodium and liquid ammonia. Now, I'll warn you in advance, this is the most complex mechanism we've done yet, but I'll try to walk you through it. So first of all, sodium, metal, is extremely reactive. In fact, if you've never seen it yet, go on YouTube and look up sodium metal in water. There's a lot of great videos of it because it'll explode in water. It catches fire, and if you've got a big enough chunk, it will actually explode. So sodium metal can't wait to give up its electron. Then what happens with that is that electron gets added. Now I've got a single barbed arrow because it's one electron moving at a time to my alkyne, and then this bond breaks and moves over here. So now at this point, I have a radical on this carbon, and I have a lone pair on this carbon, so there's a negative charge. This thing is called a radical anion. And it's very high energy and very unstable. But the reason that it forms in the first place is because sodium is so reactive. So now, this molecule can grab a proton off of ammonia, and now I'm just down to a regular radical, which are still quite reactive. And now a second electron from another sodium metal comes by and adds to the first one. To give a negative charge, which can then grab a proton off of another ammonia. And because this is stepwise, where both hydrogens are not added at the same time, they're added one at a time, that allows the molecule in the middle steps here to arrange itself so that the R groups are further apart rather than closer together. In the first mechanism, H2 on a metal catalyst, the two hydrogens had to add from the same side. But now, as we get to this radical anion, the two large groups are going to try and get as far apart as possible. And so that's what leads us, in the end, to our E stereochemistry of the product.